Thank you very much. It's a great pleasure to be here with you. I wish I could be in Tokyo. I'll be there in the fall, certainly. So today I'm going to talk about DeSci nodes and how we can accelerate research with composable and reproducible publications. So the scientific record is our greatest achievement. It forms this vast tree of knowledge that we've been building for thousands of years. However, today it suffers from loss of artifacts. We lose code, we lose data, we lose all the bits and pieces that make science reproducible and reusable and verifiable. It has unsecure PIDs, persistent identifiers, that are brittle, that rot, that can break. The scientific record itself has problems around content drift and link rot because the internet wasn't designed to solve for these issues. And it's because of that, it's not verifiable. It's difficult to find the data, to access the code, to reuse these components. They get lost. We lose them in hard drives in universities. And this creates a huge problem. And as we know today, there's a raging replication crisis across many fields of science that call whole shoots of our tree of knowledge into question. And finally, the tree of knowledge is not fair. FAIR stands for the FAIR principles, means findable, accessible, interoperable, and reusable. These are the principles of best practice in building the repositories of tomorrow. Today, our unit of knowledge is this so-called version of record. This is when you publish a manuscript as a scientist. It's published by a publisher. It's essentially a PDF file with a DOI, that's a PID, with a cross-ref metadata in Web of Science indexing. That's our unit of knowledge today. So how does it work? In the background of our work as scientists, there's a giant scientometric machinery. This is the brainchild of Eugene Garfield, a famous sociologist in America during the Cold War era, who essentially created citation tracking. So how does this work? You have at the very lower level, you have scientists that are knowledge creators. We send our manuscripts to publishers who are knowledge curators. They're running these very, very complex tech platforms that are very expensive to maintain. And that entire business is essentially more than 40% of scientific publishing today is controlled by four big publishers, as you know. And this forms a syndicated system. This data is fed into analytics providers who also play the role of meta curators, for example, the Web of Science or Scopus. And this data that's being indexed by these databases then end up before the eyes of funders, grant agencies, institutions, the committees that work for our promotions in the scientific system. And finally, it all trickles up to the institutions and funding providers. Now, if we pull the logs from this machine, we see there's a lot of problems. Scientific productivity is going down. There's rise in retractions of papers. There's a diminishing of disruptive and truly innovating research. So there's a lot of issues with that system as it stands currently, because it creates bad incentives for everyone involved. We're over-indexing on the manuscript, and we're under-indexing on the importance of data and code and reproducible research. At the same time, I'm incredibly hopeful for the scientific record and DeSci in general, because we're witnessing a rare moment in history. A lot of the systems and incentives that have been built behind the scientometric machinery are changing. There's the OSTP memo that mandates that all manuscripts and code and data needs to be open access. There's no more embargoes on our manuscripts. There's the rise of the FAIR principles, who are gaining more and more momentum around the world with funding institutions, with universities, with scientists themselves. The Center for Open Science has been doing a tremendous work, and they have this framework for change, which I love. There's this idea of a pyramid in which at the very top you have policy, then you have incentives, then you have communities, then you have user experience, and then you have at the very bottom, you have infrastructure. So right now the policy is clearly in place, and it's a moment that we can build all of the infrastructure, the user experience, the communities, and the incentives to improve the system, to create more reproducible research, to realign the incentives for scientists. So it's a moment of optimism. We're incredibly optimistic. There's goodwill at all levels of this of the scientometric system. So from policymakers to funders, There's a great interest in rethinking scientific publishing and sharing scientific resources from first principles. There's also a lot of work in rethinking our unit of knowledge. What should we publish in the future? What is the publication of the future? Will it continue to be the version of record with a manuscript that is fixed in time, or will it be something else? And this is an incredibly exciting time, because now we have the possibility to rethink this from first principle and to create a truly fair enabling unit of knowledge. So what does this new unit of knowledge look like? What could it be? Well, there's this idea of research object. So when we publish work as scientists, it's not just a manuscript. There's much more that goes into it, right? There's research data. There might be reagents in your bioexperiment. You might have computational pipelines. You might have peer review reports. You may have a pre-registered analysis plan. There's contributors maps. There's grants. There's video of procedures. There's an incredible wealth of resources out there that are very important to create reproducible and reusable research. Unfortunately, today, these components are very much underappreciated, and this has to change. And this idea is that all of these components need to be attached with PIDs, persistent identifiers. These are very important. This is essentially the key of the specific object, its identity, data and metadata, so that it can be reused easily and found and made accessible. So how does this work? Well, the idea is, like, where would you want to store these research objects? Should we take them and we put them on a silo on AWS in a bucket? No, nobody wants that. We should create a truly open and decentralized system where we can store these objects. And so we have this idea and this architecture that we've been building, which is called DeSci nodes, where essentially the research object itself is stored on a decentralized repository in the form of a Merkle DAG. So Merkle DAG is a secure data structure that is tamper-proof, and it allows us to essentially preserve these objects in a neutral space where everyone can interact with them in a permissionless way. And we take these Merkle DAGs and we index them on a blockchain, and that's called blockchain anchoring. And then we have an address, and this allows us to create PIDs, persistent identifiers, that are resolvable for both humans and machine in a consistent way. So you could think of, imagine if you had DOIs, and you could say, well, you know, the DOI of my research /data/measurement.csv, and you could resolve directly to the data. You could resolve directly to the code. You could have a machine actionable and machine readable scientific record. And the power of this infrastructure is that it decouples the data layer from the application layer. That means the data is immutably open. It's there. Anyone can interact with it. Any application that's built on this so-called open state repository can interact with that data, because the APIs that make it accessible are irrevocably open access. And the system is based on a history of research, which goes back to Nick Sasbo and others who have been working on this trilemma in computer science called the Zuko's triangle. And Zuko's triangle is essentially a trilemma that says that any namespace for digital objects should have 3 properties, but you can't. You can only have 2 of them. It's secure, decentralized, and human meaningful. And today, DOIs, so these are the PIDs of the scientific record, they're only human meaningful. But they're not even human meaningful because there's a schema that enforces in a way that it's not. So IPFS CIDs, for those of you that are familiar with IPFS, have the properties of security and decentralization, but they're not human meaningful. They form very, very long links, very long hashes. So how do we address that? Well, we have this system called DPIDs, which is, interestingly, the person who solved or had the intuition how to solve Zuko's triangle was Aaron Schwartz, the open internet activist. And he wrote that in a famous blog post, that blockchains actually allow us to combine these 3 properties of a naming system. And what does that mean? That means every object in your research object, your code, your data, any file you have in there has essentially a unique PID plus data, plus metadata, plus methods for every digital object. There's no limitation to it like there is today. And this allows us to have globally unique, permanent, secure, and resolvable identifiers for humans and machines. And this leads us to this idea of composable research objects stored open states. So imagine if you have a system where you have agents, you have entities that operate on these research objects that are there to certify them. Just like we have today with journals that conduct peer review and editorial assessment, we can enrich this much further by having, for example, data stewards that verify your data, that make it reusable for others, by having image certification services that go there, check the images, and send attestations that these images have not been tampered with. You can have research curation, like what we're doing with the Longevist and VitaDAO. They can send an attestation that says, well, this work has been selected, it has been selected by our community. And so you can have essentially transactions happening on these research objects stored open state in a way that is verifiable, traceable, and machine readable. And we can extend the scope of scientific validation to all the things that have been ignored or essentially underused in the current system, like verifying reproducibility, like verifying fair data, like verifying provenance. All of these things will be possible with the system of plural curation on research objects. And none of this can work if we don't make it really powerful for researcher. So this is really important. So we can preserve vast amounts of data on IPFS and protect that data against content drift, link rot. We can store it redundantly across 3 countries, 5 continents with a hot copy available. And then we can create powerful methods to interact with these research objects, because in essence, they now become computational objects. We can have PIDs as program destination. What does that mean? That means I can take a data file, for example, satellite images that's stored in my DeSci node, and I can send a program over to it using edge computing and get the results back. I could grayscale it, I could segment it, I can do all of these things and get the results back without having to download these massive data sets locally. You can also have PIDs as importable objects. So what does that mean? That essentially means you can take any PID in a DeSci node and import the content in your Python IDE or any IDE you're using these libraries that we're building that allow scientists to easily reuse these data sets, these code files, and all of these things with a simple one-liner line of code in your current interface. And most important is user experience. Again, today, if I'm a scientist and I want to share my data, I have to follow this flowchart. It's incredibly confusing. I have to go on third-party services and websites, and I have to scour the internet to find repositories that are willing to take my data. And then I have to get a persistent identifier, DOI, and then I need to send it to the editor of the journal, and then they put it on their webpage. It's an incredibly cumbersome and difficult process. It just takes time. And all of this needs to be improved. We need to make it easy for scientists to create reproducible science. We need to reduce the barriers, both technological barriers, to making it easy for them and for us to be able to build research that others can build upon. We have to integrate all the tools that we love and we use every day. The number one ask when you're, for editors, when they ask you to share data, a lot of scientists say, hey, can I send you a Dropbox link? And most of them are like, no, whatever you do, no, you have to go on the repository over there and and follow the procedure, follow the flowchart. And that just adds a tremendous amount of friction to the entire process of building reproducible research. So we have to accommodate the tools of these scientists and find them where they are today with the tools they love and allow them to combine these tools and combine all of the data that these tools yields into a coherent unit of knowledge. And we call those composable research objects that are stored open states, nodes. So I can give you a little demo of how this looks like. So where do you want to go when you're on a website like this? National Library of Medicine. Well, you want to run away. You typically are looking for like download PDF. So here we have, we can go there like, oh, finally, that's where I want to be. That's where I can actually read and consume that piece of research. You have inside that article, you'd have a PID embedding directly into the paper. You can click on that PID embedding and you can access the open state repository directly because it links there. So here you have AI generated art. You have that research object. You're in a very familiar environment. This is where you want to be as a consumer of science and research. but you also have a mysterious button on the side, which actually brings out a lot of richness on that research object. You have components, so you can have your research report, you can have supplementary materials, you can have reproducible notebooks, you can have data, you can have videos, you can have all the breadth of research outputs into a singular coherent unit that is human and machine consumable. So you can also add annotations, you can give context to your research. And you can create reproducible science easily. For example, here I have a figure with some complex graphs, some spectrometry. Well, I can go, hey, I want to reproduce this result. I want to reproduce this figure. And you have a code IDE within these research objects that allows people to go over the code, to go over the data, and to essentially explore all of the way these research results have been reached. And you can recompute them easily on the spot. And that allows us to create reproducible research. You can have data, you can have all sorts of artifacts directly into your IDE. You can access that data, you can play with it, you can send programs over it. So this allows us to have a singular content experience in a coherent unit of knowledge, a research object. And you have attestations. You can imagine here, for example, the ACM, the American Computing Association, they have badges that says, well, artifacts have been shared. So these badges, these attestations can be transacted on by research objects, and you can have group operating on these systems to certify them, to say, hey, this work has been peer reviewed, this work has been reproducibly has been verified. The data is fair and reusable, and it's compliant with the fair data principles. And the big difference here is rather than saying, well, the certification is the fact that the object is on my database and that you can't touch it. This is the current model. It says, no, that's not how we're going to do it. Now the model is the research object itself is on this open state repository where it's universally accessible, and third parties can interact with them and essentially certify them. You have history. You can actually look at these research objects and their versioning history, which is tracked with the stamp-approved data structures. You have credits. You can essentially explore the full PID graph of this research object in a very easy and permissionless way. So I can show you a couple of other features that we're working on. A little sneak peek. So I did this for DeSci Tokyo. And so you have here, this is the upcoming features. You have essentially a node drive. So what's behind these research papers is this idea of a node drive. It's like Google Doc. It's like Google Drive. It's like a Dropbox, and it's there with all of the artifacts that form your research, and that allows others to reuse it and allows you to make that research reproducible. So here, for example, I have data in my research repository. So I might have, in this case, I have some cute Shiba Inus, could have all sorts of things. I could take this piece of data and I can start reusing it and doing edge compute jobs. Essentially, I have here the DPID of that object, which forms its address, and I can use Bacalhau to send a Docker container over it to transform this image of Shiba Inu, maybe with stable diffusion, or to segment it or whatnot. I could reuse it easily. You can also import that image locally with a simple line of Python, and you could have that image now in your Python IDE. So this actually tremendously lowers the barrier to reusing these scientific artifacts. You can find a version history. You can see the details of how it works. You can see the size of the nodes. You have 6 copies. We have redundant copies. You can see the transaction receipts. You can have the entire transparent and tractable history of these research objects that are stored on a decentralized repository. So our hope with this and our vision is to create a system where research is less solitary PDFs, but become constellations of composable nodes that interact with each other, that can call each other's data, that can reuse each other's code, and that are machine readable. And this is going to be extraordinarily important, especially in the age of AI, with these LLMs rising. We need to make these research objects digestible for these models. And this is the essence of the FAIR principles. So it's both. It's not only human access, but it's also machine access. And this is what is going to allow us to tremendously accelerate scientific progress. Our hope is that by creating these systems, we can align the incentives of scientists to share their data, to share their code, to create more reproducible research, and to realign incentive towards the quest for truth. And so we work with DeSci Labs, and I'd like to thank my team, Sina, Philip, Adam, Carla, Eric, John, Shadrach, Richard, Andrew, Mike. Thank you so much for all the great work you've been doing. Also, we have the DeSci Foundation, which is a group of fantastic meta scientists. It's a nonprofit in Geneva that works with us, that we've set up, and we're helping. We are building a podcast there. So if you want to listen about, if you want to essentially learn about people that have been really deeply thinking about meta science and the scientific record and cutting edge technologies around that, check out our podcast. Also, thank you to Protocol Labs, who have been enduring sponsors and who have been working with us a lot over the years. And of course, the Center for Open Science, which have been a tremendous guide and tremendous source of inspiration for us. So thank you.